And the next item is Newton's law of universal gravitation. Okay. So according to Newton's universal gravitational law, what it says is like if there are two masses, there's a certain distance between them, then there will be a gravitational force between the two. Okay. So gravitational force is just literally by virtue of having mass. Okay. So because those two objects have like mass, like for instance, you can take the Earth and the Moon. The Moon revolves around the Earth because it constantly experiences force. Okay, constantly experiences force from between them, of course. Okay, and the Earth revolves around the Sun because there is a gravitational force that constantly pulls the Earth, and of course the Earth also pulls back the Sun with that same amount of force because of Newton's third law, action and reaction pair, right? But of course the Earth being relatively lighter, the Sun being very massive, for that reason the Earth revolves around it's like we are in the International Space Station that revolves around the Earth, not the Earth revolves around us because of the mass that we have. But anyway, if you are standing, even like you're here next to your friend, and you can imagine like there's a force between you two, right? Then if the distance between two was like 1 meter, and then now d2, some reason, let's say let's make it a little fun, d2 social distancing, now you cannot get close to your sister or your friend, not any less than 2 meters, right? So you can imagine like when you were here, you were experiencing a certain force, let's say 10 newtons of force. Then when you are here, you're not going to feel the same amount of force between you two. So this is like by virtue of having mass, because you have mass, your friend has mass. If you are standing next to each other, there is a gravitational force between you two. But it's one of the weakest forces to detect, like using any kind of sort of equipment or something. It's one of the weakest forces. But I mean, I'm not saying like it's too small, but relatively in terms of wave and things like that, to detect it in some sort of what we were saying is like it's a field force, right? So electromagnetic force or some kind of magnetic force, that kind of force you can detect it like with different equipment, but the gravitational force is really being weak to detect. It's very, very difficult like to see, but it's always there. If you feel it, like you experience mass times g because of that gravitational force between you and the Earth. Okay. So according to Newton's universal gravitational law, what he states is like if there are two masses separated at a distance of r between them, then the amount of force experienced between the two objects or between the two masses is g times m1 times m2 divided by r squared. Then this g it's an uppercase G, known as Newton's universal gravitational constant. Okay, it's not the small g that and it's a number and it's a constant. You're not expected to remember that number by heart, but it's this much. Okay, so Newton's gravitational universal constant is 6.673 times 10 to the power of -11, and it has that unit. Okay, then here that you can see it like in the previous slide. In this slide, as you can see here, the Newton's universal gravitational force, it's an inverse square distance. Okay, so it is here, it says it's an inverse square law. What do we mean by that? Like, it's an inverse and at the same time. Okay. So inverse square. So here's a good example. Let's say you know, the good old days, like you and your friend, you can usually stand 1 meter between you two. Okay, so I'm just giving you an example. Let's say between you two, the amount of force that you were experiencing between you two was, let's say, 10 newtons. Okay. Now, because of your social distancing issue, or anything that you may call it, like, the distance between you two is now usually 2 meters. That means, the distance between you two is doubled. Then how much would be the force that you guys are going to experience? Let's assume that, like, your masses haven't changed. Okay, none of you gained weight or none of you lost weight. So if the mass remains the same, then it's an inverse square law. It's an inverse square law. Like, the inverse square law that applies for the distance, of course. Now, the distance between you two increased. So from here, when it says inverse, you can literally feel that as the distance between you two increases, then the force between you two decreases. You see? That's what inverse means. Okay. If you guys try to pay attention and see this. The inverse, as R increases, F decreases. As R decreases, F increases. But in what manner? So here what we're saying is like, oh, okay, then if it is inverse, what is the inverse of double? The inverse of double is, of course, half. Right? The inverse means 1 over. Double means twice. 1 over twice is like half. So therefore, do you think the force is going to be now half? Right? So the force between you two used to be 10, and then now, because of the 2 meter distance that you usually keep between you two, and now the force is 5? Is that what is going to happen? But we haven't completed the sentence. It says not only inverse, but it's inverse square. See? Inverse square. Okay. So inverse square means the distance between you two is doubled. So therefore you need to square that double. That means now from here your R was 1 meter. Now here your R is 2 meters, because 2 meters is double. Okay. So therefore it's going to be, the force is going to reduce by half squared. That means by 1 over 4. That's what the inverse square law is. So that means the force between you two now is going to be 10 over 4, which is 2.5. Now it's 2.5 Newton. That's what the inverse law says. Or let's take it to the other side. Okay, now happy days are coming back. Now you and your friend is even closer, and then now the distance between you two is even smaller. Now usually, now you're getting close to each other. Usually the distance between you two is 0.5 meter. Okay. then how much force will you guys experience between you two? What is the inverse of half? Now the distance between you two is halved. You see the original? The original was like 1 meter between you two. Now it is 0.5. Okay. All right. Yeah, thank you. That's correct. It's going to be 40 Newton. How? How? Now that my calculation is gone. How? Because, I'll try to draw it again. So you were 1 meter distance between you two, and then the force was 10 Newton. Now the distance between you two is halved. Now the distance between the two masses is 0.5. Right. Then the inverse of half is 2, or it's like inverse means 1 over 0.5. But you need to square that. So the square of 2 is 4. So therefore your force now, the new force is going to be 4 times the original. And the original was 10 Newton. So therefore when the distance between the two is halved, now it is 40 Newton. Okay. Thank you. It was 40 Newton. It's all right. So then let's. So this is generally like a pictorial representation between two masses. You have two masses, and then if the distance between them is r, then this is the force applied by this object by m1 on m2, and this is the force applied on m1 because of m2. But those two forces are equal in magnitude but opposite in direction because of the action and reaction thing. Okay. When the earth pulls you down with 900 newtons of force, you're pulling the earth with the same amount of force. Okay. But 900 newtons of force is enough to pull you down. But 900 newtons of force is nothing if you apply it on the earth. Okay. But otherwise the forces always act in pairs, as we saw in Newton third. Then this is, you can use the Newton's gravitational equation, and you can find the value of g. G is the Earth's gravitation acceleration, the one that we know, remember, on the surface of the Earth, which is 9.8 meters per second square. Okay, that is equivalent to g multiplied by me, the mass of the Earth, and multiply that by r squared. Okay, multiplied by r squared. You already know what the value of g is like. It's 6.67 times 10 to the power of Negative 11, right? Do you have any idea like how much the mass of the Earth is? What is the mass of the Earth approximately? Any idea? Mass of the Earth is, yeah, it depends on the text, but it can approximate it as 10 times, 6 times 10 to the power of 24 kilogram. It's approximately like that. Okay. And what R should I use here? If I want to, so you can imagine this is the surface of the Earth. Okay. This is the surface of the Earth. Then this guy is trying to find Earth's gravitational acceleration. What he knows is, he knows the mass of the Earth, he knows universal gravitational, and then he knows the radius of the Earth. Do you know what the radius of the Earth is? Approximately. Any idea? Anyone? 10,000 miles? Yeah, it's approximately 6,400 kilometers. Some textbooks say like it's 6,372 approximately. 72 kilometer. You need to change that to meter. When you change it to meter, this will be something like this. Square. If you simplify this, it's going to give you that magic number. Okay. I mean, the numbers, the number may slightly differ depending on the textbook that you refer, because the Earth's radius could be a little different, the Earth's mass could be a little different, and so on. So if you apply this equation, and if you find the Earth's gravity at different, so starting from the surface of the Earth, if you go up to 1,000 kilometers above the surface, you're going to feel this much gravity. Can you imagine? That means there is still a considerable amount of gravity even if you are 1,000 kilometers above the Earth. Yep. You will experience 7.33, which is huge for a gravity. For an acceleration per second, that's a huge number. After the 5th second, you are going to drop like 35 meters per second, something like that, right? When we talked about like every second your speed increases by about 10 meters per second, right? If you're on the surface of the Earth, but still at a distance of 500 kilometers, you will still be feeling that much. Okay. I mean, it's for some other time discussion, but like you may say like, have you ever wondered like where the International Space Station is? The International Space Station, where you see those astronauts like floating in their spaceship, right? Yeah. International Space Station isn't even at about of that distance. Where is it? Okay. So, no. But if you see, the International Space Station is not even at an altitude of 1,000 kilometers. No. It's probably about 500 kilometers. Something like that. Above the surface of the Earth. That means those people that you see on the International Space Station, they still feel a considerable amount of gravity. Okay? But you may wonder, like, why then their space station not dropping straight on to the Earth? If there is that amount of gravitational force, gravity. Okay. It has its own reason, because of the speed, the escape speed. Something related to that. Okay. Okay, guys. It's like, if this is the Earth, and then if you stand here, this is of course an exaggeration, and then if you throw a ball, the ball will drop like this, right? If you throw that ball a little stronger, the ball will drop like this. Let's assume that you are one of the strongest person that we have ever seen in our life, and then you throw your ball like this, and then you literally pass the Earth. What's going to happen to the ball? What do you think? You missed the Earth when you throw the ball. Have you thought it that way? Like, what's going to happen to this ball? Look what's going to happen. Exactly. It's going to orbit. It's going to orbit. That's what is happening for the International Space Station. Like, there is an escape velocity, like you shoot that thing, then it will constantly miss the surface of the Earth. It's not dropping down. But it's going to go to orbit, and then it will keep on looping because of the centripetal force. Because gravity is not going to let you fly off to space. It will constantly keep you pulling towards the center of the Earth. Okay. So one day, like when you feel empowered, try to throw a ball as much strong as you can. If you ever made it like to a certain speed that it just passes to hit the surface of the Earth. Okay. Yes, definitely. That's what is happening because of that escape velocity. But otherwise, there is gravity. There is a misconception that many people see those guys and floating in their space station, and they feel that like, there is no gravity there. No, that's not the reality. Even they are not at a 1,000 kilometer. Even at 1,000 kilometer height, you experience that much of gravity, which is considerable. We're experiencing 9.8. For somebody who's really 1,000 kilometers above us, will experience that. That means if you drop a heavy object from that, it's going to come straight down to the Earth, definitely. Of course, because of, a lot of, velocity and things like that, it will fragment and so on and so forth, but definitely it will come back. Okay. So, I'm not going to go to Kepler's law and things like that. So concept-wise, this is what we have for Newton's gravitational law. Having said that, like, as usual, let's go back to our problem-solving session. Okay, then let's try to reinforce like whatever we have been talking in the last I don't know how many minutes. Let's try to see a few examples before we wrap up the class. Okay. Any question? Questions? Solve a few problems. Okay. So E11 from the text. So E11, I'll read it for you. So E11 states two masses are attracted by a gravitational force of 9.6 Newton. What will the force of attraction be if the distance between the two masses is quadrupled? So E11 says two masses attracted by gravitational force between them is 9.6 force. Okay. What will the force of attraction be if the distance now, so D or R, is quadrupled? If R is quadrupled, then how much would be F? That's what you are asked to find. So remember the inverse square relationship between force and distance. Answers? Anyone? Nice. So that means like now you understood like what the inverse square relationship between force and distance is. So originally like the objects were at certain distance. You can imagine any distance you want, but if they were originally the distance between them is r, then now 4 times of r. Okay. Inverse square. So if the distance is inverse means like if it is a 4, a quadruple, then it is 1/4 of whatever force that you had. Okay. So quadruple, double, those are like twice, 4 times. If it says triple, then the force relationship will be 1/3 squared. So that's what the force, you can call this one the new force is going to be that much. The old force was 9.6. I mean, yeah. So therefore it's going to be 1/16 of 9.6. Okay. Plug in that in your calculator. If you want, I can verify, but the answer is 9.6. I mean 0.6, right? Valid approach. It's like you imagined Fg equals, say it like G m1 m2 divided by you had r squared. Now the new one is Fg equals G m1 m2 over 4r squared. Or you can imagine r is between them was 1, then that's fine. If you do that, then you could literally that if you compare this with this, and this force is already known, 1.6. If you compare those two values, so this is like your old one, this is our new one. Okay, so if you compare those two, how do you compare them? You can take if you want, you can take the ratio between those two. It's going to be literally the same answer. Your F old divided by your F new. That means if you take the ratio of between those two, gravity cancels out, mass cancels out, radius square cancels out. The only thing left is 1 over r. 1 over 4 squared. So that is 9.6 divided by r squared. 4 squared. So this will lead you to the same answer. Okay, you can start from the very original equation of Newton's gravitational law, and then you can find like your F new. Then you will end up with the same value for F new. But as a shortcut, just simply using the definition without going into the details of like the equation, then you can always try to answer it that way. This is because this is an easier way. Otherwise, the other one is a little more advanced, but that's perfectly valid. Okay. So let's go ahead and then see E13. It's going to ask you a similar question. Okay. E13, I'm going to read it for you. E13 says two masses are attracted by gravitational force of, so you can consider this as your force old or force 1. You can imagine it like originally 0.28 Newton. Now it states like distance between, if distance between the masses is halved, now how much would be your new force? All means like you can imagine, if you want, you can imagine the distance between them was 1 meter. So this is like when they were like this, consider it as your old force, they were like that. The force is like that. Now the distance between them is halved. You can consider this as a new force. How much would be the force? First of all, so you can say this is R now, this is R over 2. All right, anyone? First of all, you can ask yourself like, will the force increase or decrease? When you get close to each other, the force increases. When you move up away from each other, the force decreases. Something that you need to answer is like, will the force increase or decrease? And the second item that you need to keep in mind is like its inverse. What is the inverse of half? The inverse of half is 2. Okay, so therefore your new force, I'm trying to answer it like just from a direct kind of understanding in terms of inverse distance square relationship, not like from the perspective of like the original equation, because I thought this way is a little simpler. So the net force is the new force, like we called it new. Okay. So the new force is going to be now, so your new force is going to be larger than the old force. Why? Because now the masses are closer. if they were 1 meter apart at the beginning, now they are half a meter apart. Okay, so the inverse of half is of course 2. So therefore 2, but the relationship is like inverse square relationship. That means the inverse of half is 2, and then you square it, and then you multiply that with the old force. Okay, so therefore you have 4 times the old force is 0.28. Okay, so it has been noted, then multiply this force, it's going to be 1.12 newtons of force. Okay. All right. So it's like this: inverse square of the distance. The new force that you get is the inverse of. So, but now the new is like halved. It says halved. So then your new force is going to be 1 over 1/4 of the old. But dividing a fraction by another fraction is the same as multiplying it by the inverse of it, right? Or by the reciprocal of it. Then this is going to be literally 1 times 4 over 1, because the reciprocal of this is 4 over 1 multiplied by f all. Yes. Okay. So that's why, like, when it says halved, that's what I was saying, like, it's easier, like the one that I wrote in black. It can be an easier approach. It takes you, like, you read the problem, and then if it says half, then what is the inverse of half? Then the inverse of half is double, or 2. Then based on that, you square that number, and then you multiply that by the old number. But if you want to go back to the original equation and how the relationships come in, you can still use the half at the way it is, and you plug in it as in, because it says like the square of the inverse. It means like square of inverse means 1 over the half. So this is the half part. But when you square the half, it's going to be 1 over 1 over 4. But what is 1 over 1 over 4 mean? Right? Then it means 1 times 4 over 1. Because, like, that's the only way you simplify a fraction. When a fraction is divided by another fraction, the result is the same if you do multiply the numerator part multiplied by the inverse of the denominator. Then as a result, what you will have is your new force is going to be 4 times the old force. And our old force is given as 0.28. So this is 0.28. So multiply 4 times 0.28, then the answer will be 1.12. Okay. So most of the questions here, like instead of the hardcore multiplication, because the hardcore multiplication involves g and so on and so forth, we try to keep it like in terms of inverse distance and things like that. One last question before we wrap up the chapter and the topic. So E15 states the following: the acceleration of gravity on the surface of Jupiter is approximately 25 meters per second square. What is the weight on Jupiter of a woman whose weight is on Earth 150 pounds. So it says like G on Jupiter is 25 meters per second squared. And the weight on Earth is what? It says 150 pounds. We know that G on Earth, we can use the one that we are usually approximating, the 10 meters per second. Now the question is like, what is the weight of the person or the woman on the surface of Jupiter? Even though it's given in pounds, it's fine. It's the question is, it's a matter of proportioning. It's not a matter of calculation. I mean, doesn't involve like any of the formulas. You rather like try to use your own imagination. Okay. First of all, will the lady's weight be larger on the surface of Jupiter or lower on the surface of Jupiter when it's compared with that of the Earth? Okay. If we mentioned this like in the previous chapter, like if there is a higher gravity on the surface of a certain planet, your weight will be higher. Of course, your mass never changes. Okay, so this weight is given in pounds. It's the force. Anyone? One is 60 or 600. Anybody else? So first of all, will the lady be lighter on Jupiter or in terms of weight? Or larger? Look at Jupiter's gravity. You know that the mass never changes, right? If the mass never changes, then the higher the gravity, the larger the weight, right? So as you can see here, gravity on Jupiter is 25, which is how many times larger than on Earth? 2.5 times, right? So therefore, her weight will also be proportional to how much the gravity increases. So it's going to be 2.5 times the weight on Earth. Okay. Because like when you go to a certain planet, if its gravity is twice larger than the gravity of the Earth, your weight doubles. Your mass never changes. You know, it's just multiplied by the gravity. So in this particular case, you may say like, what did you get? 2.5. 2.5 is like gravity on Jupiter is literally, in this particular case, it's 2.5 times gravity on Earth. Because one is 10, the other one is 25. So therefore the weight also is proportional. So it's going to be 2.5 times 150. Okay. Alright. That's going to be 300, 425. Alright. So it is 375. Okay. So with this we are concluding the chapter. Okay.